Okay, so Bode plot, I actually put up something, but I think I set the permissions for that video incorrectly. I don't know how many of you were able to access the video. How many tried? Rest didn't bother. Some issues were there. Yeah, but others didn't even bother seeing. Yeah, very enthusiastic class you guys are. Okay, so I'm not going to finish this. I think you know how to do this, right? Finally, how does the transfer function look? How does it look? Siddharth, did you do this? Show me. Priyanshu, how does it look? Okay, so those who have the Bode plot remain in class, others leave. Okay, so we have to enforce some discipline. I can't be like a fool speaking and nobody does the work, then there's no point. So Anuja, just go around. If they have the Bode plot with them, let them stay. Otherwise, let them leave. Anyway, they can listen to the recorded video. Come. Okay, maybe some of them have done it in the exam or something. Okay, we'll call a couple of fellows. Come. Yes, how does it look? Shift what? What do you mean shift? Huh? So what will happen? So finally, describe the output of that device. Come here and draw it. Come. You guys are so late. 8 o'clock class, you can't come in at 8:10. It's the beginning of the semester. No, that's wrong. That's wrong. Siddharth, come correct this. Where's the eraser? It's here. What is the difference between that and this? No, I don't quite understand. You just have to add those 3 lines. Will it look like this? That means you guys not bother to do it at home. I am very clear. If you don't do the work that is requested, you will not follow this course. And there is no problem. I'm not going to keep the quiz easy. We'll just grade, and whoever doesn't clear the course will remain here, right? Like 5 minutes of work. It's quite depressing for a teacher to come and people don't do what has been asked. What else do you have to do? And this is the second time. I had told you guys to do it and come for yesterday's class. Then I told you guys to come and do it at least for today's class. Anurag, what is the correct plot? Sorry? By a step. No. Somebody else come and finish this. Madhav. Just erase that and then at least a rough shape, and then we'll do the correct, we'll clean it up. Correct. And what would be the flat portion? What would be the gain there? What gain? What would be the level of that flat portion? 40. Think about that. So I'm going to add these things, right? So add here this and this. What will you get? Right? It will be here. Right? So you will be 0 here, and then whatever, and anywhere in the middle, right? So this entire thing will become 0, right? This region you have a 0, you 40, and you have this line which is going to continue downward. So you just take this corner point and then fit things with the slope. So this corner point will come here, right? And then at 10, right? What would happen to this? Right? This one at 10 would be minus 60, and you have a plus 40. So basically you should come minus 20, correct? So but from here you should that way, right? And then similarly from here, that would be the final answer. This is not hard. This is 12 stuff, even less than that. It's just 3 logarithms you have to add. You guys know, right, that between the computer science batch and the EE batch in the little course there was a difference in the average of about 15 to 20 marks. There's a huge difference between the amount of effort you guys are putting in and the amount of effort your classmates in other branches are putting in. Bar a few people in this class, everyone's just sleeping. And if you are in a new IIT, unless you work hard and work harder than the people who are in the other IITs, you want to get good jobs and good placements. It doesn't take much for a person. We can get an interviewer here, but it doesn't take much for a person to figure out whether you actually understand something or not. Right? If somebody comes and just asks you, I'm giving you a low pass filter, it's Bode plot. You should be able to do it immediately. If you don't, the guy knows, okay, there's no point. Right? So we're just wasting time like this. I don't want this to repeat. If I ask you to calculate something and come, better do that. Otherwise, don't come to the next class. Anyway, the lectures are recorded. You can listen to the recorded one. Okay. The point of recording it is so the class is more active, which means you guys have to do more work and come. Okay, let this not. Okay, so let's proceed on. So today I'm calling this as lecture, but this is effective the first teaching lecture of this course. And today's date is 4th. Okay. So the philosophy that we will follow in this course is that we won't go too much into how the device itself operates, because that is the content for a more detailed course on solid state devices, which you will do next semester. Okay. So here we'll assume that you have a vague idea as to how it operates. We'll see what the terminal characteristics of the device are, and then we'll see how to make circuits using those devices. Okay. Why does a diode behave the way it is? That you learn semester. Okay. Let's get into that right now, because we won't have time there. Alright. Okay. So what diode? Let's start with what's called an ideal diode. What is a diode? Akshat, what do you think is it? Okay. How many terminals does a diode have? How many terminals do you think a triode will have? 3. And then a tetrode, pentode, 5. Right? These devices do exist. And so the diode is one of the simplest of the nonlinear devices that you have. So far all the devices you have seen have been linear, right? In EC 101 all the devices were linear, right? Okay. So an ideal diode, it has 2 terminals, the anode, the cathode. Right? And what is the characteristic of an ideal diode? Let me say that I ignite my voltage V like that and current I this way. What are the properties of an ideal diode? I'm sure you thought about this earlier. Say I am going to plot voltage on this axis and on this axis. How would an ideal diode? Yes, correct. So when the voltage is less than 0, right? The voltage is less than 0, what do you expect? When voltage is than 0, what do you want the current to be? You want I to 0, right? So basically when voltage is less than 0, you want to be there, right? And then what about the other situation? This is an ideal diode. Okay? There are many technologies to realize a diode. Semiconductor technology is one way of making it. Before semiconductor technology became popular, this is before you were born, I was born, the semiconductor technology became popular towards the end of the World War. So 1948, when the first semiconductor transistor was invented. Before that, the technology dominated, or the entire World War, the technology that dominated electronics was the tube technology. So you had vacuum tube, right? So we won't get into that right now. We can do possibly in the next. Okay. So depending on the technology, the real diode that you have in that technology will have a characteristic that looks similar to this, but not exactly this. But for circuit analysis, let's start with what's an ideal diode first. Okay. All right. So for V less than 0, I 0, then okay, that's a little more unideal, but let's just stick to completely ideal. Correct. So how do you write that? Okay, let me just draw that. So what I want is that for, right, I want that. So how do I write that mathematically? So it's actually easier to write it this way: when I greater than 0, V equal to 0. All right. So this. So if I were to keep this as a two-terminal device, right? This is effectively. Is it an open circuit or a short circuit? Right? So this is an open circuit. Yes. So for yes. So at the moment the voltage becomes, so okay, forget about V equal to I equal to 0. Forget about that situation. Okay. I think what you're asking, what is the situation when V equal to 0? Right? Forget about that. Because the real diode anyway, that is not going to really happen. Okay. So forget about, so as long as V is infinitesimally greater than 0, your current, basically you have shorted input and the output. So whatever the external circuit requires, that amount of current will flow. Okay. Forget about the singularity of transition region. Okay. All right. So what happens? So I equal to 0. What is the situation? Sorry, I greater than 0. This is a short, right? What is the resistance in these two regions? What is the resistance here? Resistance here? Infinite or 0? Infinite. And what about the resistance here? Okay. So assume this to be the ideal diode, and I promised that we are going to look circuits, right? This is a course on analog circuits. So we just take a simple example and then come back to this example many times later. But let's just take one example. So let's have, for example, some kind of source. I'll draw the voltage waveform. I put in an ideal diode and I have a resistor. I am interested, say, in the voltage across the resistor. Okay. So let me say that this is V in of T. That's your diode. This is some resistor, and I want V out of T. And to make definite, let me out V in and V out. So let me say my V in is let me say V in is this. What would V out be? How do you analyze this circuit? The bottom parts will be, but why is that? Okay, but how will you analyze it systematically? This circuit? Use this, so that you possibly know function of this diode, right? But this is a nonlinear element, right? So depending on what your current and voltage are, right, the characteristics are different. So how would you analyze such a circuit? You can start, example, assuming that I is 0. Okay, assume this is an open circuit, and then go backward and see what is the situation under which that happens. Okay. So if I assume, so first take the situation when I go. Okay, what would that mean? If I is 0, then this particular in that case, this will be sitting at this. So let me say this is let me call it as, say, X. What would be Vx? Vx would be no tell me exact number. I is 0. Okay, let me put it this way. It becomes clearer. Sorry? 1 by I? No, I grounded that. So Vx is 0, right? If I is 0, Vx is 0. Right? So if I is 0, Vx is 0. And if Vx is 0 and this device is basically off, what should we? So what the problem you are trying to solve here is, you are trying to find out for what value of Vin will I be 0, right? And this is Vx is sitting at 0 volts. So the moment this particular point goes below 0, this device is off, right? So when is that? Whenever Vin is less 0. So basically, whenever Vin is less than 0, V out would be equal to 0. Right? So that would be the situation. Then you consider the next situation. What's the next situation? What's the next situation? So you finish this one, you look at this. Correct? So when would this happen? It has to happen whenever this is not happening, right? So in this situation, V is 0, right? V is the voltage of the diode. So if V is 0, basically whatever is in the input will come to the output, right? So your Vx is equal to Vn of t. So basically the output is going to follow the input there. Clear? So what is this? What has diode actually done? Right? So this is, you have seen this possibly earlier, right? So this is basically acting like a half wave rectifier. Why do you call it a rectifier? Okay, what is the value of the AC component of the black? Sorry, what is the, for the black signal, what is the DC component? V in I only the DC component. What is that? What is the DC component of a sinusoid? Siddharth, what is the DC component of a sinusoid? 0, right? What is the DC component of V out? Greater than 0 or less than 0? DC is just the average. So the average of the black signal is obviously 0 because it's symmetric, at least if I have drawn it symmetric, right? And what's the average of this red signal? It's greater than, right? Which one? So when, what is V here is the voltage across the diode. If we just analyze this situation where I 0, right, and then you found out what is the what's the value in under which I is 0. You have done that. Now I am considering situation when V is 0. V is the voltage across the diode. So the voltage across the diode is 0, right? Then what can you say about Vx and Vn? Vx is equal to Vn, right? And when is the voltage across the diode 0? Whenever there is some current flowing. That is the so when basically this is the situation when I not equal to 0. Right? So you have already analyzed the I equal to 0 situation. You analyze the I not equal to 0. Okay. So basically for these nonlinear circuits, you have to take both the situations and then analyze. With some practice, you will be able to directly look and tell. Then you won't go through it so systematically. Okay. Okay. Let's go to the real diode. So maybe we can. Okay. So how does the real diode look? Depending on the technology, right? So let me have my axis first. Okay, and I think we already described the equation of the diode in the previous course. Anyone remembers? Right, so we said I equal to some I naught. Let me call that IS in this course. Okay, exponential of V by Vt, that's not threshold. Okay, minus 1. Does the minus 1 come inside the exponent or outside? What is Vt? Vt is your Boltzmann constant into temperature divided by electric charge, right? And this is approximately 25 millivolts at 300 Kelvin. Okay, this is called the thermal voltage. What is IS? Yes, more precisely it's called the reverse saturation current, and you will see why that is the situation now. Okay, typically in good diodes it's of the order of say picoamps, right? Pico is 10 power minus 12, right? So 10 power minus 12 to 10 power minus 15 for a good diode. But if you have like a discrete device that you buy, and make some circuits with them, maybe it's 10 power minus 9. It depends on the diode. Okay. All right. So how does this characteristic look? So it's basically an exponent, right? So for positive voltage, it's fairly easy to draw, right? It's an exponent, right? So at 0, what is the value of this at 0? 0. Okay. For positive values of V, right? It's essentially the exponent, right? So right, and what about negative value? So what is when V becomes less than 3 times Vt? So consider this exponent. Okay, and look at the situation when V is less than say 3 times V. What is the exponent? What is it equal to? This is exponent of minus 3, right? What is exponent of minus 3? No. What is exponent 3? Somebody have a calculator? Calculate. Huh? No, V by Vt. Right? 0.0 49. So is 0.049 large or small compared to 1? So you can basically drop it, right? So for V less than Vt or V less than Vt, that's what's the usual threshold that people talk of, right? So in this region your I is effectively equal to minus Is, right? So unfortunately when you draw it here you will be able to see it. Okay, so we'll zoom it, but on this plot, right, it's going to, it's a smooth function. We'll zoom it. Okay, so that is the diode action as given by this equation, right? Actually maybe I motivate this correctly. Yeah, this is the wrong way of doing it. In that we should start with this equation and then draw the plot, right? Because the equation itself is a model. A real diode is not a diode whose performance is governed by this equation. A real diode is a real diode, what you get in the market or what you get when you fabricate, right? So a real diode, you will see, you can model the real diode by this equation. This equation is not what defines a real diode, because as I will draw another point now, it will become clear, right? So what happens if V becomes very, very small? If I keep the voltage, what do you think will happen? Yes, Akshay? I can't hear you. Current approaches 0. No. Minus Is. Have you heard of a thing called breakdown? Yes? So what breakdown? So if I keep reducing E, right, there will be a situation where the current goes down like this. Okay? And this, do you think this breakdown can be explained by this equation? No, right? So this is a model. The real diode is the real diode. So the way I motivated it is not possibly the correct way of doing it. Okay? So there is a diode like this, and you can model the diode by this equation. In fact, we forgot to put in one factor, which is a source of non-ideality, and that's actually a factor called n there. Okay? And we'll see what n is. It's a number, maybe. So for an ideal diode, n is 1. Certain diodes, n is 2. Right? It's usually between 1. Okay, so that is your real diode. Which one? No. N does not govern down. You can actually find out what n governs. It's an interesting problem. We'll come to that. Okay. So, yes, correct. Doesn't predict the breakdown. Correct. So, what is the diode? How is the diode made? The simplest diode is to have a P and an N region, corresponding to right, and so the normal course of flow is when you have positive voltage to the P side, negative voltage to the N side, and current goes from the P to the N side. Okay. However, if you apply a reverse voltage and you apply a high reverse voltage, something happens inside. Okay, there are two mechanisms. One mechanism called Zener breakdown. In Zener breakdown, basically electrons from NP. It's a tunneling process. In other kind of breakdown, it is called as avalanche breakdown. In avalanche breakdown, you have what's called an avalanche process, which is if you can excite an electron to have sufficient energy, if you can excite an electron to have sufficient energy, then when that electron collides with the lattice, it can generate one electron, one hole. Okay. Electron plus hole charge is 0, right? Electron has a negative charge, hole has a positive charge. Don't get into too much of the details, we'll go into it systematically in the next course. But just remember, the electron has a negative charge, the hole has a positive charge. So the electron, if one electron, energetic electron, comes and collides with lattice, it can, for example, generate electron and one hole. So it is not, charge wise, nothing has changed. Now if it is sufficiently energetic, that electron, which is the secondary electron which is generated, can have sufficient energy to go and knock out another electron and hole. And each of these can go and knock out another electron and hole. It's like an avalanche, right? What's an avalanche? Ishita will know about avalanches. Yeah. So, right? An avalanche is something that starts small and then picks up speed in very short time, right? So, an avalanche process can also explain breakdown. So, in different diodes, you can either have Zener breakdown or avalanche breakdown. Okay. So, let's not go there right now. So, you know that there exists a break. Okay. Now, the correct way of looking at this is to no, we want equivalent circuit. So, we should have an equivalent circuit for the forward operation. So, this is called the forward operation. Forward bias. And this is called reverse, right? We want an equivalent circuit for the forward operation mode and an equivalent circuit for the reverse operation. Okay. Let's start with, before we go anywhere, let's just look at this reverse region alone, but in a scale that is zoomed in. Why do I have to zoom? So, what's the typical value of I when the device is on? This you should be able to answer from your experience in the laboratory last semester. Assume that, so you have played with some kind of diode, all of you. What diode did you play with? LED, right? All of you made things with LEDs. That's also a diode. What was the typical current through that LED? Milliamps, right? Of the 1 to 10 milliamps. That's the current. And I am telling you that when V is less than 3 VT, your I is minus S, and IS I am telling you is, in a diode, picoamps, in a not so good diode, nanoamps. You plot nanoamp and say 1 milliamps on the same scale, right? And you go to a log scale. On a linear scale, you cannot plot milliamp and a nanoamp same scale and make out any difference. The nanoamp will appear to be 0, and that's what this is. That's why the reverse region appears to be 0. This watch is fast, so we'll take 5 more minutes. Right? The actual time is 46 or something. Okay. So, what was I saying? Yeah. So, if you want to look at just the reverse current, what do? You choose a different scale only for the reverse region. And this is something which a lot of people get confused, because if you look at the textbook, slyly say forward axis one scale, reverse axis a scale, and then at that junction things will as if there is a kink. So you go back, look at the textbook that we have, you will follow what I am saying. Okay. So if I were to only plot the reverse current, right? If I were to only plot the reverse current, it will actually appear to be something like, right, before the breakdown, right? And what would this value be? That would be minus IS. And how would the breakdown appear? right? It's almost flat, and then you would something like this. What is the axis here? Just same axis, right? So the voltage is still measured that, and the current is measured this way. But I am just looking at the reverse bias region of this diode. Okay. So come to this again. Okay. This is, so I'll call the now let's go to what we need for this course, which is basically the equivalent circuit for a diode. For a real or ideal diode? Real diode, right? I'll take the simplest one and then we'll stop. Okay, let's take just the forward option. Okay, let's take the forward operation. And the current was 0 for, and then it picks up and it goes up. So the simplest way of approximating this is to that, say, I want to define an on current, right? I want to mentally have a picture of when this diode on. So say I can look at what is the voltage at which this current, this device allows 1 milliamp to flow. In an application, it may be a different voltage, but say it's 1 milliamp. Okay, so I look for where 1 milliamps on this plot. So 1 milliamp may be here. Okay. The exact value may differ from application to application, but as you will see, what we are going to define will not vary that much, even if the 1 milliamp changes. Okay. I can justify that. So right, and find out the volt at which the current, so I call this my voltage, this is current, right, and this is designated as V with a gamma, and this is called cut in voltage. You will find that different books define this cut in voltage differently. Okay, this is a good definition that works for many applications. Let's go with this definition. It may be slightly different from what the textbook that we are following suggests. Okay, but I prefer this definition, and there's nothing really wrong in engineering. As long as you're reasonably correct, it's okay. Okay, so what this is basically saying is, when the current is say 1 milliamp, I want to know what is the voltage. So I do that because one simple approximation of this device would be that the simplest approximation that so that is my V gamma. The simplest approximation for this curve could be that I am going to 0 all the way until V gamma. Okay, and then vertical or V gamma. Okay, so this So we started with an ideal diode. How did the ideal diode look? Ideal diode was like this. So now I have introduced the first deviation from the ideality, which is that instead of this transition happening at 0, the transition is happening at cut in voltage. Okay, all those other applications can come later. Start from, we know the idea, we in mind we know what the ideal diode should look like. We also have the real diode characteristic. Let's approximate that real diode characteristic to various degrees of idealism. And, just the last thing, and I am going to close. So this V gamma itself for many this will be in the order of 0.7 volts. It depends on the material. Okay, so if the material is silicon, which is what is most common, it will be roughly around 0.6 to 0.7. For this course, we will get as 0.7. If it is say germanium, it will be lower. Okay, so for now, let's assume that cut in is 0.7. Okay, so I would like you guys to read the first say 10-15 pages of chapter 1 or chapter 2 of the textbook. Okay, all of you have access to the book? Yes, no, maybe? No. What are you planning to do? You can purchase that book. It's a good book to have. It's about 800-900 rupees. It's not. No, I went and checked again. It's 825. Oh, you ordered it 600. Oh, okay. Then I saw, I think the print is. Okay. Because when I bought it, I thought it was 600. Then yesterday I was looking at the back and it looked like it was 800. Then I thought I made a mistake. So online it's 600. Okay. New Year offer. Cedra and Smith. That's a nice way of getting. Okay. So let's close here. Tomorrow we have class at 10 o'clock. Is that right? The original. Okay, go check the timetable. Whenever the timetable says we are going to meet, we will meet at hour. I think it is 10 o'clock, but go check your timetable. Okay, and then in the afternoon we will meet for the